Now we've come to the next part of Module 1, Part 7. Another measure of spread that we're going to talk about is called the standard deviation of our data. We mentioned in the last section the range. The range is one very easy way for us to measure how wide our data set really is. And it's very easy to find. All we have to do is take the largest value and subtract the smallest value. So with two data sets, set A and B, if we were to find the range of both of these sets of data, we'd see that the first one has a range of 6 and the second one also has a range of 6. So you can see it's very easy to find, but if you look at these two data sets, you can also notice that they are very different. And so the range really doesn't tell us a whole lot, even though it's very easy to find, about the data set, especially if we have extreme values within that data set. So it doesn't always give us a true picture of data. Both have the same range, but have a very different spread. So we need another way to calculate spread. One thing that would be helpful for us is for us to figure out how much every piece of data is straying away from the middle, which would be our mean. In other words, symbolically we could show this quote-unquote deviation from the mean as xi minus x bar. Xi represents every individual data value within our set, and x bar, of course, is the center or the middle number. If we could do this for an entire set of data, this would give us something very interesting and helpful. So let's take that first set of numbers that we have. In calculating the standard deviation of these numbers, we would first need to simply lay out these numbers. Well, and first, actually, we need to find the mean of that set of numbers. So we add them all up and we divide by the number of numbers, which is 7. And we see that 35 divided by 7 is 5. That's the mean of my set of numbers. Now, if we take each one of these numbers and calculate how far they are from that middle value, we have another set of numbers. These set of numbers actually represent the distance each data value is from the middle value. And in fact, we can also look at which ones are to the left of our middle and which ones are to the right. These represent, in other words, the distances each data value is from the middle. Now, if we were to find the average of this set of numbers, that would be helpful. But it actually works out to be not so helpful, because the sum of these numbers, of these distances, is actually 0. That's because by definition, the mean is the middle, and so when we subtract the distances to the left and to the right, they end up being equal distances, and their sum is 0 because we're adding positives and negatives. So we need to get rid of that middle number. We need to get rid of these negatives. One way to do that is to square those numbers. The squaring of a negative number always makes it positive, and so in doing so, we've gotten rid of all the negatives and the positives. Well, actually, we've gotten rid of the negatives and we still have our positives. Better way to say that. Now, if I find the sum of these numbers, because remember, sum, if we're wanting to calculate average distance from the middle, is important. I want you to notice the symbols down here. These may look really complicated, but they're really not. This little symbol here is the sigma symbol, capital sigma, and it always represents sum. So by putting sigma and then putting parentheses around these differences squared, that means we're finding the sum of the squared distances from the mean. The sum of these squared distances is 28. Now if I take that number and I find its average, we take 28 and divide it by the number of numbers, or the number of distances in this case, and there's 7 of them, we get 4. Now, unfortunately, 4 is not the average distance, it's the average squared distance from the middle. So we need to take this back into the units that we were originally dealing with. In other words, we need to unsquare this number. So if I take the square root of 4, I get 2. 2 is the average distance each of these data values differs from the middle value of 5. This tells me a lot about the average spread of our data. This one number, standard deviation, which is the 2 here, tells us on average how far each data value differs from the mean. So very large standard deviation values mean we have a large spread in our data. Small numbers mean that we have very little differing from the middle, from the mean. Putting these into formulas gives us some somewhat complicated looking formulas. I want to draw your attention over, first of all, to these ones on the left. There's two formulas given, and I want you to sort of ignore the first ones up here for now. We're going to look at population variance. This was actually the first number that I came up with for. If you'll notice, the sigma here is the sigma of xi minus x bar squared. So it's the sum of all the squared values divided by n, which was my number of values. This one formula demonstrates that process that we just went through. Notice that this formula is not a typical formula in that we can just plug in a couple numbers and get the result. We actually have to create a table of values, find all their differences, square all those differences, find that sum of those squared distances, and then divide it by n. So this actually represents the entire process we just went through. And notice that we never took the square root. That's what we do over here. Before we take the square root, that was called our variance. So in the previous example, this number was a 4. Once we took the square root of that result, we got 2, and that was my standard deviation. So this formula represents the process that we just went through. With all that said, let me draw your attention to the ones up here. You'll notice that these are very similar. In fact, the top part of these fractions is exactly the same. The only difference is the number that's on the bottom. This is one of these weird, complicated mathematical things that we really don't want to get too much into. However, with that said, these formulas we apply when the numbers that we are dealing with are from a sample rather than a population. With sample numbers, these are usually used to try to estimate population numbers. When we're interested in finding out something about a population, usually that population is too large for us to talk to everyone within that population. We're going to talk a lot about this when we get to inferential statistics down the road. But for now, samples are generally used to estimate population numbers. And so because our sample is not the whole population, what we find is if we subtract 1 from the size of the sample, that is n minus 1, we actually get a better estimation of the population number. So for standard deviation in general, this is the number we're actually going to be using, because most of the time the numbers that we're looking at are actually sample numbers, not population numbers. So in general, about 90–95% of the time, we're going to be using this formula, where we actually subtract 1 from n before we divide. Some properties of standard deviation. Number 1, S, or sigma, which is the other symbol, measures the spread about the mean and should be used only when the mean is chosen as a measure of center. We never want to subtract median or mode from our distances, or from our values. And so standard deviation and mean go together, just like the 5-number summary goes with median. When we're measuring spread, if we've chosen median as our measure of central tendency, we use the 5-number summary as our measure of spread. If we've chosen mean as our measure of central tendency, then we are going to use standard deviation as our measure of spread. If S is 0, or greater than 0, that tells us something about our numbers. If s is 0, then that means there was no spread at all. And in fact, that means all our observations would have the same value. As the spread increases, so does the value of s. The bigger the s, the more spread of our data. The smaller the s, the less spread of our data. Thirdly, s is going to have the same units of measurement as your original data. So if our original data was in inches or miles or feet or meters, then s will also, we can interpret as being in those same units of measurement. And fourthly, just like s, just like the mean, standard deviation is not resistant. A few outliers can make s really large, really fast, and therefore we need to be cautious about when we use it. Standard deviation can be found using your calculators. And for the most part, that's how we're going to do it in here. For really large sets of data, we will probably turn and use Excel instead of our calculators to calculate standard deviation. We're generally never going to do it by hand. So, the way we would calculate this using our table is to put these into a list. If you remember, the list is under Stat and then Edit. So we put these numbers into a list. Always remember that when you clear a list out, you want to highlight list 1 or list 2, whatever it is. So you want to hit the up arrow, and then you want to hit clear and then enter. That will clear out your list. Never highlight L1, L2, or L3 and hit delete. That will actually delete list 1 or list 2 completely from your calculator, which can be fixed. For references to these things, make sure you watch the calculator video that was given earlier. So put these numbers into your list, and then we hit Stat again, and we go to Calc, just like we did before, and we pull up the one variable stats. In that list of numbers below X bar, you're going to see a sigma symbol, which represents the population standard deviation, and below that you're going to see the S symbol. That represents the standard deviation if you're treating it like a sample. Again, most of the questions in WAMAP you're going to treat as a sample, and therefore you're going to use the standard deviation S instead of sigma, which is the other symbol that you saw back here. Let me pull us back here actually. This is the sigma symbol, which represents standard deviation of a population. This, if you remember, this also is a sigma symbol, and it always means sum in mathematics. This is just a capital sigma, and this is a small sigma. Well, that pretty much does up our lesson for standard deviation. You can feel comfortable in going ahead and practicing the exercises associated with this once you've read the text. Thank you.